All right, this question 24 reads, the diagram represents the pattern of stationary waves formed by the superposition of sound waves from a loudspeaker and the reflection from a metal sheet not shown. W, X, Y, and Z are 4 points on the line through the center of these waves. Which statement about these stationary waves is correct? An antinode is formed at the surface of the metal sheet. Well, this gives us an opportunity to review what is meant by a node and an antinode, because the existence of nodes and antinodes is really what characterizes a stationary wave. On this diagram, we could see where, let's just say that this wave here was the outgoing wave, and then it got reflected by that metal sheet that's not shown, and this was the return wave. So those two waves, they meet, they are coherent because they're coming from the same source. So this is typically how we're going to get a stationary wave, by using sort of one source that's reflected and then it comes back and interferes with itself. So these places here would be the nodes, and these places here would be the antinodes where there's maximum displacement. So we can see there's a series of nodes and antinodes as a stationary wave. Now, a sound wave, remember, is a longitudinal wave. And so there's a paper cone, there's sort of a coil in here that's moving a paper cone that's pushing air. And so the air particles are moving parallel to the direction of energy transfer. A note of A above middle C has 440 hertz. It oscillates 440 times per second. And so an air particle moves backwards and forwards 440 times per second, crashing into other air particles. And that's how sort of sound propagates. It's tough to draw that, sort of waveform. And so we draw it as a transverse wave, but we know that sound is a longitudinal wave because of what it's doing. It's sort of pushing other air particles and they're moving left and right as the energy transfers along that same direction, sort of from left to right across the screen. So at the metal sheet, remember, an antinode is maximum displacement. Really what's happening here is the particles here are moving the most left and right. Here they're not moving at all. They're just sort of in place. And here they're moving a little bit left and right. Here's the maximum displacement left and right. So that's sort of what's really happening, but we're showing it with this transverse wave because it's easier to draw. So take care to eliminate choice D as the air particles oscillate perpendicular to the line WZ. So the line WZ is this one. And if you look at the wave form that they've drawn, it does look like that's true, that the particles are moving, up and down as the energy is going left to right or along that line. But that's not the correct answer to this because we know it's a sound wave. Sound waves are longitudinal. That was one of the key learning objectives with how do the particles move in these two types of waves? Okay? If we shake a string, if we did the wave on a string, right, then those particles of the string move at right angles to the direction of energy transfer. That's transverse, but sound is a longitudinal wave. So at the metal sheet that's not shown, it has to be a node because, the particles can't move through the metal sheet, right? And so there has to be a node at the metal sheet. So an antinode is formed at the surface of the metal sheet. We can eliminate that as an answer also because it has to be a node that's formed there. There's no displacement occurring if there is a piece of metal. The air cannot sort of move through it, right? So to achieve this stationary wave, we'd really have to move this metal sheet until we just got it perfect to where, it would be a node. And you'll see that when we use something called like Meld's apparatus, which is kind of a vibrating string, we can move sort of the distance of the string as a way to achieve sort of more nodes and antinodes. And so sort of the length of the string and most of the distances won't work. It has to be sort of half wavelengths, right? So each one of these is a half wavelength. If this wasn't at a node, then we wouldn't get the interference pattern. Right, so we can sort of adjust that and explore that experimentally. This is why only certain notes are allowed on musical instruments, right? You sort of, you can only pin down the string, sort of like you have a string of a certain length, or you can pin it down in certain places. So all the harmonics are sort of the allowable frequencies. We'll look at an example of that on the next question, which is about a bugle. A node is a quarter of a wavelength from an adjacent antinode. So if we look at that and we think about, well, here's an entire waveform like this, Let me draw it in pink to distinguish it. So the entire wave goes from equilibrium up to the crest, back down through equilibrium to the trough, and then it repeats, right? So that's the point. That's the adjacent, identical sort of point on the wave. And so that's the wavelength from there to there. So here's a node. And if we go a quarter of a wave, that gets to the antinode. And so indeed, a node is a quarter of a wavelength from an adjacent antinode. That checks out. So D is correct. Let's disprove C. The oscillations at X are in phase with those at Y, X and Y. So when it's a stationary wave, the particles are either in phase or they're out of phase. All of the particles that are on this part of the string, and they're showing you sort of the string at two different parts of time right now. Sometimes, you know, you'll see a figure like this and it's showing you, well, the string can actually only occupy sort of one point in space at a time, right? And so it'll sometimes be shown like, well, there's where the wave actually is, but a moment later, it's gonna sort of be down here. And so you can sort of see the standing wave kind of like that, but the wave isn't actually in two places at once. You know, it's a moment later, it's gonna sort of be down here. And so adjacent loops are always 180 degrees out of phase. Like that particle is 180 degrees out with that particle, that one. So all these particles here are moving up while all these particles are moving down. So here's a nice noteworthy statement that if I was a student of physics sort of learning this for the first time, I would write this down in my notebook. I would say the particles in adjacent loops. So you kind of see a stationary wave as like these loops. All the particles in adjacent loops oscillate out of phase, 180 degrees out of phase on a stationary wave. All the particles in adjacent loops in a stationary wave oscillate or vibrate 180 degrees out of phase with each other. Keep that in mind, okay? You'd have to go over to the next loop to find particles that were in phase again. So while all these particles here are moving up, all these ones are moving down, they're 180 degrees out of phase, but the next loop over, right? So not the adjacent loop, but the next one after that, every other loop will be in phase, right? So all these are going up, while all these ones are going up, not the adjacent one, but the next one after that. And so that's why we could eliminate choice C. The oscillations of X and Y, we can see are occupying adjacent loops, right? The particles that would be there. And so they're not in phase, they're 180 degrees out of phase, right? So that word needs to be correct. So we can eliminate choices A, C, and D clearly and use it as a chance to kind of explore the physics and really get to that choice B is the correct answer. I mentioned that only certain allowable frequencies, that's the idea with stationary waves. We have something like a musical instrument called a bugle, a long tube with a mouthpiece at one end. The other end is open and flared as shown. A musician maintains stationary sound waves with a node at the mouthpiece with a correct embouchure. To use a little musical vocabulary. And an antinode at the other end. The lowest frequency of sound that the bugle can produce is 92 hertz. Which different frequencies of sound can be produced by the bugle? And if you think, oh, well, a good bugle player can produce any range of sounds, that's not true. That would violate the laws of physics. So there's something called the first harmonic, which is the fundamental frequency, which they've already given us. It's 92 hertz. And you can see every single answer choice has that. That wave would look like if the mouthpiece is a node, okay? So the particles are not gonna move left and right there. That's where the mouthpiece is. And the flared end here is an antinode. Then the first sort of frequency that we could get would be if the wave just kind of opens up. Remember, we're looking at an entire waveform, but we're only seeing this much of it. We're seeing sort of 90 degrees of phase. 1/4 of the wave, right? So it's going from equilibrium up to crest, but that's where the mouthpiece is. That's an antinode. And so the lowest sort of frequency, the longest wavelength, right? So this is we're only seeing a quarter of the wave. The whole wave doesn't even exist. The whole wave would be like that, right? Longer than the whole bugle. But that doesn't mean we can't get a musical note. We don't have to have a whole wave to get a musical note. We could get a note at 92 hertz, a quarter of a wave. And so that's the key to thinking through this. We're cramming more and more wave into the same fixed length of our bugle, right? It's not a trombone where we're changing the length. That's how a trombone can achieve different, notes. But the bugle, the skill of the bugle player, like, is in their ability to sort of fit more waves into here by producing different sort of notes using that old embouchure I mentioned, right? The note at their mouthpiece. And I think maybe the way they hold it too, you can manipulate that. I'm not really sure. All right, so what's the next one? We're restricted to node, antinode. We need waves that look like that. So if we kind of think about waveforms, we could maybe get to the next one. It would have to go, now it couldn't be open and closed, right? We couldn't get like half a wave. So a quarter of a wave works, right? So this is like 1/4 of the wavelength, and that gives us a frequency of 92 hertz, okay? We couldn't have half a wave because that would be node and node, right? If it sort of pinches down like this, in other words, this wouldn't be a good waveform because it doesn't have antinode. But if we got to maybe the next antinode there, well, that's a quarter, a half, 3/4. So that's like 270 degrees of phase. And so I'll draw this down here. This would be, there's our first quarter, and then it's going to go back down, but then it's going to open back up like that. So the next sort of waveform is going to look like this. So again, you can try to sort of sketch the bugle kind of around it, where there's our mouthpiece, right? This is our flared end with an antinode. We clearly got that. And let's think about what we got now. We got a quarter, a half, we got 3/4 of the wave here. So if this much of the wave was 92 hertz, right? We know that this corresponds to a frequency of 92 hertz. Then we could say, well, then if we're fitting more wave into the same given length, then the wavelength has, sort of decreased. The frequency has gone up. And so this would be 92 plus 92 would be 184, but that's not an allowable wave. And so let's eliminate sort of that choice. 138 can eliminate that, right? It's got to be 92 plus 92 plus 92, 276. And so it's either choice C or D. We've got to carry it to at least one more to see what, sort of it's going to be. So note the allowable frequencies go up by half wavelength, starting at a quarter, when it's this kind of a situation with one end is a node and one end is an antinode. So the next one would be open, close it, open it again, and then I have to close it, I have to open it one more time. So this would be antinode there, it goes through a node, and then that one. So again, it's the same length bugle, and now we've got, there's our whole wave, there's 4/4, but we've got another quarter of a wave, and so this would be our 5/4 of a wavelength. There's one wave and another quarter, right? So see the pattern, 1/4, 3/4, 5/4 wavelength. And again, we're sort of fitting more of the wave into the same space. And so that's why we're getting higher frequencies, the higher harmonics. The fundamental frequency is the lowest harmonic. And so this would be the fundamental frequency. The next harmonic would be 276. And then 5/4 of a wavelength. Again, what are we kind of doing here? We said, well, if 1/4 is 92, just mathematically, we can say, well, then 3/4, multiply that by 3 to get this number, multiply it by 5, right? How many of these 92 sort of hertz do we have, or how high of a frequency would this sort of wave be? So it's going to be 92 times 5, or 460. So there's the next harmonic. And then we could keep going and say, well, 7/4 and 9/4 would give us these frequencies. But right away, we can say that we've eliminated choice B because that's not the next one. So which different frequencies of sound can be produced by the bugle? 92, 276, 460, and then these would be the next higher harmonics. And so those, the first 5 harmonics on this bugle, choice C.